Welcome to Computing on the Edge with Kubernetes. My name is Steve Mansfield. I'm an IoT software architect with Jabil. Today we're going to talk about deploying a Azure IoT Edge with Kubernetes K3s. K3s is a lightweight, small footprint deployment of Kubernetes. The agenda is we're going to first talk about IoT in the factory today, look at how Jabil is implementing IoT today and some of the challenges. We'll talk about IoT Edge, Azure's IoT Edge. That's the deployment platform that we actually implemented the solution on. And then we'll talk about Rancher's K3s and some of their persistent store servers, and then have a quick demo. So should be interesting. So Jabil is a contract manufacturing company, about 260,000 employees, 100 factories in 30 countries, and we have tens of thousands of manufacturing lines. Not so much an advertisement for Jabil, but just trying to give you a size of how big Jabil is. It's a worldwide company, so our IoT deployment is a worldwide, enterprise-wide type of deployment. It's quite a large one. Our mantra is the product delivers real-time production data securely and conveniently in Jabil. That's all we do. We don't try to analyze the data. We don't try to do analytics or any kind of AI or anything like that on the data. Our approach is to simply capture it, package it up into a common data format, and then securely send it to where anybody in Jabil needs the data today. What we're using IoT for is really to improve manufacturing efficiency, looking at material supply chain management and flow. That's as materials flow into the warehouses, we're tracking that information. As materials flow to the machines, we're tracking that information. And as the product, as it's being built, flowing through the factory, we're also tracking all that information. Then there's real-time production process management. We actually can manage the process of these machines. We can stop panels from going into certain machines if they're the wrong serial number, or if the job is not set up correctly, or we can redirect them on conveyor systems to go to workstations to be reworked, things like that. Also, machine line status. We constantly looking at our factories to make sure that we're getting the optimal output from them in terms of the lines being up and the efficiency of the factories. Now, this whole thing, these requirements, the large worldwide enterprise deployment of this kind of thing, the kind of data that we're collecting, has created a number of challenges. And the first is in the industry that we're in, the SMT industry, or surface mount technology, electronic PCB manufacturing business. There's not a lot of standards for communication and capturing the data from these machines. They're all Ethernet connected, they're all TCP/IP, but they all have their own protocols. They have their own data standards, naming and tagging and things like that. So that's a big problem for us in terms of the number of different types of machines and manufacturing machines that we use at our factories today, is being able to capture it with all the various different protocols. Also, our factories are located throughout the world, like I said, but some are located in geographies where the internet is not as robust as we might like. So we have to be careful about how much data we can actually push through the pipes, internet pipes, through the factory. So it causes a few challenges there and has influenced the design. Another big issue is no two lines in Jabil look alike. Every line is different. We're a contract manufacturer. We have thousands of customers. We're building tens of thousands of different products. So each line is customized for that particular customer's product and how we build it. So the configuration, the way they look, how they're set up, the types of machines, the organization of the line, everything is different. We have to take that into account as in our overall solution. And then finally, high availability and data resilience is a key component of the solution. These lines cannot stop. They run 24/7, 365 days a year, constantly running. The only time we take them down is a third shift on Sunday, so for maintenance and repairs and things like that. So they're constantly running, and when a machine goes down or a line goes down, that's a pretty significant thing. So that's another key component of the software solution. The another thing we did was we didn't want to make one giant piece of code, monolithic piece of code to be able to do this. We knew this wouldn't work because of all the differences in the line. So as we examining things, we kind of noticed a design pattern, right? That each of these machines had their own specific interface. So we had to divide a microservice that sat in front, of each machine, containerized, a Docker containerized microservice that manages that machine interface. The data from each of the machines is very different, and its organization, its type is different from machine to machine. So we had to take that data and then convert it into a common data format that was more useful throughout JBL. In our case, we converted everything into JSON. Also, too, we try to create a common semantic model so they can help the programmers that are developing the applications. They didn't have to spend so much time worrying about, which manufacturer the data was coming from. We tried to create this common semantic model so that the data all looked common to the applications. And then finally, the application interface. Every application, we have multiple applications that are running in the factories that are relying on this data. And then we have other applications, analytics, quality data, enterprise statistics gathering and things like that that run at other facilities. So sometimes, so the application interface pushes the data to the specific application that it may be looking at. And then finally, security. As I said before, a lot of these machines don't have security, so we have to provide some pretty secure interfaces in front of them so to keep the hackers away. So this was this common data pattern that we saw, and one of the interesting things about this is we created these containers that we called immutable Docker microservices. The containers are generic, and we define the behavior and the properties of the module using desired properties in the manifest. So this really helped us a lot in that we didn't have to, we created the behavior and the properties of the container at deployment time and not at software right when we wrote the software or when we built the software, but actually when we deployed the software is where we define the behavior and properties. This really made the problem of developing all the code for these environments much simpler, and also reduced down the number of containers down to about 50 to 60 containers needed to support all the machines in our factories. So once we had this kind of common data model with the immutable Docker containers and the setting the behaviors at deployment time, we were able to basically build a deployment where for each line we could define the containers needed for each of the various machines for the line, and then set the behavior for those containers at or modules at deployment time, and then push that data to the various factory applications or to the corporate data lake where some of the other applications could access it. And this allowed us to handle a lot of lines without having very large kind of clunky software. It gave us a very flexible, very easy to change just by changing the manifest. We could completely change the behavior of the software running on very specific lines. So this really worked out well. It was fortunate that we kind of saw these design patterns and were able to put together this kind of model. But it certainly created some challenges for us, and that we have a lot of containers now to manage. For each one of these machines, it really wasn't intrinsically high availability. That had to do with a lot of the machines didn't play well in an enterprise environment because of the protocol, the types of protocols that they were using, and then just managing the whole factory, right? The number of on-prem servers and things like that we needed to manage this. So we started initially. Our development platform is a product called Azure IoT by Microsoft. It's a hybrid platform. It can run in the cloud. It can run also on-prem, and it's basically broken up into two parts. In our implementation, we're using it as a gateway. Like I said, the machines do have Ethernet connectivity, so we don't need small little devices in front of them that are kind of converting the data and pushing it onto a network. They already have the network part of it done. So we capture that data from them on the network as part of our gateway, and then we push that data to our various factory applications and also the the data lake, the factory data lake. The IoT Edge implementation is, like I said, broken up into two parts. There's the cloud part that's called Azure IoT Edge, and then there's actually the device or the deployment part, the part that we work on that runs in the factory, and that's called the IoT Edge device. The hub basically manages all of the data going from the cloud to the edge device itself, and it's broken up into kind of two parts, the manifest and the digital twins. We push the manifest or the deployment template to the hub. In the IoT Edge device, there are two key modules. One's called the IoT Edge Agent, and the other one's called the Edge Hub. The Edge Agent is looking for changes in the manifest in the IoT Hub. When it sees a change, it downloads those changes, and then from there it decides what to do. So the IoT Edge is actually doing the Edge Agent is doing all the orchestration, for us. It's actually doing it, running it on the device itself. So when it detects a change in the manifest, declarative deployments, right? When it detects the changes, it goes and kills containers, downloads new images, and then or updates desired properties for these containers. So it's a symbiotic relationship between the two. You've got the cloud component, you've got the IoT Edge component, and they both work together. The hub manages data back and forth. So all of the desired properties that we set the behavior and the properties of each of the modules that are in the deployment template are extracted by the hub and then pushed to the various containers. So that updates their behaviors and properties. And then also, if any of the containers are pushing data to Azure, they'll push it through the hub and to the IoT Edge hub. And then from there, it can go exercise various Microsoft applications that are running in the cloud. So this is a basic IoT Azure Edge. It's a single Moby. It's running Moby in the background on the IoT Edge device here. So it's not a Kubernetes-like environment. It's a single Docker type of container deployment environment. This was good in the beginning, but as we began to grow, and deploy more and more factories, we started running into a lot of issues of trying to manage all these containers, running on this IoT Edge device. So in 2018, Microsoft came up with a way to run IoT Edge on Kubernetes, which was a big plus for us because all of a sudden we could now be able to leverage the high availability capabilities of Kubernetes. Plus, it was much easier with namespacing and things like that to be able to manage the high number of pods that we'll be working with. It was a very innovative way that Microsoft implemented this. They created a CRD that extended the current Kubernetes API, and that those APIs, basically what they did was they took the existing IoT Edge deployment template and they converted that template to a Kubernetes manifest. So we could take the existing deployment templates that we had today without any changes, not a single change whatsoever. We could deploy them to Kubernetes. They would get converted to a Kubernetes manifest. It would then download all of our images into the cluster with no code changes whatsoever. There was the requirement of a new component called an IoT Edge D, which is a daemon which manages the relationship between Azure IoT Edge and Kubernetes. Remember, in the IoT Edge environment, Edge Agent wants to be in charge of managing the deployments, but it can't do that here. I mean, of course, Kubernetes, it's the responsibility of Kubernetes to manage the deployments. So they developed a proxy, or they call it a sidecar, that sits within each of the IoT Edge containers, and that proxy works with the IoT Edge and manages capturing all of the security credentials from Kubernetes, and it manages Edge Agent in terms of just Edge Agent now just manages the application within the namespace. So it's really innovative solution. It didn't require any changes whatsoever to our code or any of our containers. It didn't require any changes to our deployment templates. So it was a pretty neat solution for us. Kubernetes has a fairly large footprint, about 6-7 gigabytes of main memory. We went and looked. We found the Rancher Kubernetes K3s, which is a certified distribution of K8s. It's the DNA of it. All comes from K8s, but it's actually a deployment, right? Just like you have uh, Linux. Linux Ubuntu, or say Linux Alpine, right? Alpine's much thinner than say from Ubuntu. Same thing here. They simply took the standard K8 deployment, uh, removed a lot of things that we just didn't need in an IoT kind of edge type of deployment, and made it about half the size of a standard Kubernetes deployment. So this thing it's a certified production for production workloads. It minimizes the size of the footprint, on the device, and that's important because we're an edge device. We're resource limited, and so that reduction in memory footprint was very important. And it's optimized for IoT edge applications, so it was perfect for our implementation. So it was something that worked very well. The first time we implemented it, we needed persistent store. Obviously, we were going to be using HA, so we had to have persistent store. So for the servers, we initially implemented a Postgres SQL high availability persistent store for the servers, and we used a standard Linux NFS in an HA mode for persistent store for the agents. So we tried this first. We got it working. It worked pretty well. We were, pleased with it. But, we had 6 additional VMs that we had to provision for the factory. It was extra work to provision these things, and so we kind of wanted to find something that had a little bit of a smaller footprint. So we looked around and found that Rancher developed a couple of extra projects or products called etcd Embedded, and of course etcd is something we all know and love from the Kubernetes side, but they took it and embedded it within the control plane within the servers, so that we didn't have to have or set up or deploy and provision an etcd server, or in our case a Postgres SQL server on the side. It's all integrated in. It's a simple command to integrate it in. We don't have to set anything up for it. So it was a really, really neat thing to have for the servers. And similarly for the agents, Rancher has a product called Longhorn that provides persistent store for the agents. Again, it's HA and it runs across the multiple agents, and provides multiple PVC types for persistent store for the edge agent. And that was important because if you recall the daemon, the IoT Edge D daemon, it requires persistent store. If that node that daemon is running on fails, it needs persistent store to be able to redeploy itself to a different node. And you need a unique type of PVC called a read-write many, and so they support that in here. So that saved us a lot of work. And again, it was a very easy deployment for us. It works very well, and it's HA. So this was our final implementation, and we've started testing on it in this environment, and thus far it's working really, really well. Kubernetes K3 is production ready. The Rancher Longhorn is also production ready. etcd is still in test, but in the next couple of months or so, they'll be production ready with that code as well. So this turned out to be a very good platform for us, a very good edge IoT platform for us. So let me let's go ahead and do a demo. For this demo, we're in the Azure portal, and we will now move over to the Cloud Shell. I'm actually running 6 VMs, 3 for the servers and 3 for the agents, along with some test applications that I've got running in there. So when we go over to the Azure Cloud Shell and then take a look at the nodes that we have. Okay, as you can see, I've got 6 nodes in a what I call a 3x3 configuration. It's using 3 masters or servers and 3 workers or agents. And you can see that the masters, each of the masters are running embedded etcd, and that's key for for managing the masters. The workers, although don't have showing roles here, they are running the rancher, NFS PVC persistent volume store for for the workers. So why don't we look at the pods next? So here's the pods. You see down here at the bottom, IoT Edge. That's an important, we've talked about that, the daemon. Edge Hub, Edge Agent, and then we've got 6 other pods here that are running my application. Now IoT Edge is running on worker 1. Okay, let's go find another worker 1 that has a counter running on it. So notice 1B here is also running on worker 1. So what we're going to do here is we're going to kill or stop node 1, and then watch how Kubernetes recovers with these embedded persistent store components. So let's go back to the portal. Let's go find worker 1. Okay, there's worker 1. All right, and like I said, I'm going to stop it. I'm not going to kill it because then I have to redeploy it later on. So we'll just stop it for now, and we'll wait until Azure is completely stopped the virtual machine. Okay, so Azure's now stopped the VM. Let's go back to the Cloud Shell. Let's, oops, timed out. Let's go restart a new one. Okay, let's make sure we got, let's look at our nodes. Oops, we got to reset up the certificate. Okay. Okay, you can see here my worker 1 is not ready. Let's take a look at the pods. And you can see here that the worker 1 has terminated the IoT Edge, which is the key one, and it looks like it's restarted it on worker 3. That's good. And also it's terminated counter 1B, okay, and started it up on worker 3 as well. Let's take a look at counter 1B. Let's make sure that that one is still running. So let's look at the logs. Okay. Type in the container here. Okay. I think I got the right one. Oh, I didn't copy over the total pod name. There should be an X at the end here. Okay. Okay, so you can see here the logs. It just outputs the time and a counter every second. So it looks like that counter successfully recovered, and most importantly, the we able to restart the IoT Edge 1 on worker 3. If that persistent store was not working, the Rancher Longhorn NFS was not working, the IoT Edge would just stall and it wouldn't reload those containers that were terminated in pod 1 or worker 1, excuse me. Okay, so now let's go back and say let's kill or stop. Let's go stop server 2 just to make sure that everything's good with our server. So let's go to master 2, okay? And with master 2, let's go ahead and stop that one as well. Okay, let's stop it. Yes. All right, let's wait a little bit here for Azure to complete stopping that VM. Okay, so Azure's now stopped the server here. We can see that it stopped. So let's go back to the shell. Okay, and let's check to see what's going on with our nodes. So we can see that the master 2 is now not ready. Okay, let's look at the pods. Okay, and we can see everybody's running. Still, IoT Edge down here you can see is running still on worker 3. There's no more worker 1. Worker 1's been terminated. Let's go and just check. So everything seems to be working here real well. So what we've demonstrated here is a 3x3 configuration of servers and agents. We've shown that the Rancher NFS persistent store is working correctly with the correct loading of the IoT Edge, and we've shown that killing the master continues to keep the system up and running. So that's it for the. Okay, just one last thing to what is the resource utilization, right, for this deployment? So we see here on the center here, we've got the CPU utilization. And the third column here, the percent user. These are what the pods are. They're counter A, counter 1A, counter 1B, counter 2A, 2B. So these are using about anywhere between 4 to 6%, almost 7% of the system CPU, or excuse me, user CPU utilization. I come over here and I look at CPU utilization. What's the total amount of CPU being used? And it's running anywhere between like about 7 to 15%. So what we see here is if we subtract out the total user here, it looks like Kubernetes and the persistent store is using approximately about 6% of the overall CPU utilization. So that's a good number. It's a very reasonable number for Kubernetes. I'm using a very low performance VM, Azure VM instance, 2.3 gigahertz Xeon processor. It's only got one vCPU. 3.5 gigs of RAM, just had enough, just barely enough, and some 7 gigs of HDD. So relatively low performance processor. These numbers would probably get a little bit better if I was running something faster. And in the real world, I would be running something much faster than this. Let's check out our memory as well. On the fourth column here, the KB mem used. So it looks here, the masters. This master, I think, is when I killed it. And so we're running about 3.3 gig per master. That's pretty. That's what the Rancher folks said that this would run in, about 3 gigs. And then also the workers are running at about 2 gigs each. So both the CPU utilization is very reasonable, about 6% or so, and the memory footprint is about 3 gig, a little over 3 gig, 3.3 gig for the masters, and about 2 gig for the agents. So this all looks very good. So recommendations, first of all, when you're building this kind of platform, especially for IoT and factory environments, everything's got to be HA. Recommend you implement the control plane load balancer ingress. And what that is today when we were remoting into the cluster, we were remoting into server 1. Its IP address, but we recommend, or Rancher recommends that you put a load balancer in front of the 3 servers, so that if server 1 goes down, when you try to remote into the cluster, you'll have server 2 or server 3 available to make your kube control commands. Always be aware, especially in the IoT world, the dynamic IP addresses of Kubernetes, ingress and exgress, right? So be mindful of that. Resource, make sure from an agent standpoint, we're trying to limit everything we can. The servers are running on a minimum server kind of environment, so we want to be careful. We want to put the right taints on the servers so that we keep the user applications off the servers, and they're only running in the edge agents. So also workspace names is very, very handy, especially for us because we have so many lines and we use workspace names to kind of segment all of the various lines, and it makes it easier because we have a single manifest for each workspace, and it works very nicely when we're adding new lines or making changes to new lines. We just have to deal with a single workspace as opposed to a whole cluster, a whole factory cluster. Also look at the installation hints, the hints that Rancher has on their product. I can't emphasize more the K3 security review. Kubernetes, its security model is somewhat open. Kubernetes doesn't have any real intrinsic security issues, but they tend to leave things somewhat open to make it a little bit easier to install. So you've got to watch out for those sort of things, but also too, watch for your image registry. Make sure you got that thing locked down real good, so people aren't getting images in there that might not have been tested or may have security issues, or you haven't done your security audits on them. Make sure you control the access to it, right? So that when people are deploying those images, they've been tested and they've been gone through a security audit to make sure that they're good containers. The orchestrator, you always want to have the latest orchestrator, right? And make sure you get your orchestrator from a reliable source. So that's important. Of course, security for your hosting infrastructure, your storage systems, and your container daemons. So always do a good security review on this, just because of the nature of where Kubernetes is today on security. Also, a lot of good third-party tools out there from a deployment, resource management, single pane of glass. There's a lot of nice stuff out there to be able to use. So in summary, we've developed an architecture for a very production-ready, high-availability edge cluster. It's optimized for IoT edge applications. It's a really good Kubernetes solution for Azure IoT Edge. We're very pleased with it in terms of its overall architecture, its simplicity, and its just smoothness and good data flow. Whenever you see an architecture that has good data flow, that's a good architecture. We're using the lightweight Rancher's K3s distribution. Okay, small footprint. Little resource utilization for the platform, which is you're always resource limited when you're out on the edge. And it's an integrated solution, all production ready stuff. Microsoft Azure IoT Edge, Rancher K3, embedded Etsy, and then Rancher Longhorn. And then it's a very simple installation. It took a while to kind of figure it out, but once we figured out the installation, it was pretty simple. So really good platform. We're very pleased with it. Special thanks to Steve Busby and Venkat Yella from Microsoft. They were very, very helpful to us in understanding some of the nuances of IoT Edge. Same thing with the Rancher folks, Jared Elder and Mark Abrams were very helpful in helping us really optimize the platform for an IoT platform. And then also my JBill management, Zolt Varga and Jacob Williams, for letting me go implement a pretty cool project that that's going to have worldwide deployment implications. So special thanks to those folks, and I really appreciate it. So also there's some useful web links here for those that if you want to go back and do some more research, kind of see where I got a lot of my information and stuff. So finally, thank you very much, and have a good day.